For Lab 5, I decided to observe and model motion of collisions and the energy transfers and changes that occur. I found a YouTube video of two objects of equal mass, one at rest and the other approaching it at constant velocity. I used the energy principle and Newton's second law to understand and create a computational model of this motion, which revealed that the kinetic energy of the collision was equal to 0, thus causing this to be an elastic collision. Here's a clip of the video I observed from YouTube. You can see that the cart to the right sits at rest while the cart to the left approaches it at constant velocity, and once they collide, we see the cart to the left slow down greatly and the cart to the right moves in the positive x direction at a similar velocity to the velocity of the cart on the left. From Tracker, I extracted the data for the time versus the position on the x-axis for both of the objects and made a graph of the information. The graph displays what I just explained about the motion of the objects. You can see that the position of object 2 remains at 0 until here, where object 1, which was moving at constant velocity, collides with it. After that, object 2 moves at what appears to be the same velocity that object 1 started with, and object 1 slows to an eventual halt. You can see that there are a few places on the graph where the data does not look linear, and this is mainly because of difficulty finding the center of mass on Tracker. In order to create a computational model of the observed motion, I used the data from Tracker as well as the fundamental principles. First, I inputted the initial conditions including the mass of the objects, the initial position of object 1, and the initial velocity of object 1, which was calculated by subtracting the position that object 1 was at right before the collision from its initial position and dividing this by the change in time, thus finding the velocity to be 0.325 meters per second. The initial velocity of object 2 is 0 because it is not moving until object 1 comes into contact with it. Later in the code, I showed the new velocities after the objects collided. To find the final velocity of object 2, I used the final position of object 2 and from that subtracted the position right after the objects collided. Then I divided this by the difference of the corresponding times that went with this data and got that the final velocity of object 2 was 0.299 meters per second. In the code, we are assuming that object 1 stops after the collision, and so its final velocity is 0. Newton's second law in the form of the momentum principle can be modified to find its change in position, which is where the final position of the respective object is equal to the initial position plus the velocity of the respective object times delta t, and this can be seen here in the code. For this lab, we need to use the energy principle. This principle states that the total change in energy is equal to the change in kinetic energy plus the change in potential energy, and this is all equal to work. We are not accounting for potential energy or the outside forces on the system, so these values will be 0. Therefore, the change in energy is equal to the change in kinetic energy, which is 1/2 times the mass of object 1 times the velocity of object 1 squared plus 1/2 times the mass of object 2 times the velocity of object 2 squared. Here is this represented in the code. Here's how the code looks when run. On the graph to the right, the blue line represents the motion of object 1 and the red line represents the motion of object 2. The green line is the total change of kinetic energy, which is at 0. I'll talk more about the significance of this green line later. This is a comparison of the graph in the code versus the graph from Tracker. Both graphs look similar, however there are some discrepancies. One important thing to notice is that in the graph from the code, the initial velocity of object 1 is equal to the final velocity of the object 2. This is caused by the conservation of momentum, which says that after the collision, the velocity of the first object is transferred to the second object. It is similar to in the Tracker graph, however, as discussed earlier, the initial velocity of object 1 is a little faster than the final velocity of object 2. And you can see that right here, how the slope is a little bit different. And so this could be due to many factors including friction, the release of energy to the surroundings, and the masses could have been slightly different while we were assuming that they were identical. In addition, in the code we assume that the second cart's velocity would become 0 immediately after hitting the cart, and this can be seen by the fact that the blue line is horizontal right here. However, in the Tracker graph it takes more time to become horizontal before it comes to a stop. Some causes for this is that the objects may have not been completely equal in mass, or there was some energy that was transferred to the surroundings. Now I will go back to the significance of the green line, the total change in kinetic energy. The line is at 0, and this means that for the model there is no change in kinetic energy, thus causing this to be a perfectly elastic collision. In conclusion, a perfect model of the principles calls for an elastic collision, but in reality there are energy changes and forces that cause discrepancies in the data.